uh, the transformer operating at no load condition, and we have assumed an ideal transformer. Ideal transformer means a transformer in which there is no loss taking place, means neither core loss nor copper loss, right? And also the leakage flux effect has been ignored, but later on we will also consider the influence of the leakage flux as well as the various losses on the performance of the single phase transformer. Then we have established the relationship between the turns ratio, which is also known as transformation ratio of the transformer, with respect to the voltage and currents at the two terminals of the transformer, right? So today we will extend this part, and we will discuss about the phasor diagram and equivalent circuit diagram of single phase transformers at no load condition. At no load, we are taking this case, means ideal transformer at no load condition, just for better understanding about the concept of the transformer. But actually in every transformer we have some load connected to the secondary side, right? Whether it is a high voltage side or low voltage side, normally loads are connected on the low voltage side, which we also known as the secondary winding, right? So the purpose of drawing the phasor diagram is to establish the various quantities, like you can say applied voltage, which we have considered as V1, then core flux, induced EMF in the two windings, that is E1 and E2, and the current flowing through the both windings, right? The voltage drop can also be expressed in the form of phasor diagram, in the phasor diagram. Now this phasor diagram will basically provide a basis to draw the equivalent circuit of the transformer, right? From where we can determine the various performance characteristics like voltage regulation and efficiency of the transformer at different power factor loads, right? So basically we have to draw the equivalent circuit because we need to calculate the different performance characteristics. Some of you have also calculated it in the lab classes, like efficiency of the transformer and voltage regulations, but there are different methods. So for that we need to initially draw the phasor diagram, right? So I will again redraw the uh, figure which we have considered in the previous class, that is a core type transformer. uh, just draw it. This is your V2, this is V1, N1, and the generated induced EMF is E1, E2, and 2 is the turn of the secondary coil, and there is a flux in the core, which we have denoted by phi, right? So you know that the magnitude of the induced EMF, that is E1, in the primary winding will be approximately equal but opposite to the applied voltage V1, because we are considering here an ideal transformer. So in ideal transformer we will also ignore the winding resistances. However, if it is present in the system, even if it is present in the system or winding, then the value of the impedance of the winding is very less, right? It is designed in such a manner that the impedance of the winding is very less. Therefore V1 is basically you can say approximately equal to minus E1, right? तो अब जैसे कि मान लो कि इस पूरे सिस्टम का वी हैव टू ड्रॉ द फेजर डायग्राम, right? And this current was at no load condition, we have considered I naught, which is the exciting current. So you can see that the flux is a common parameter in the transformer, which is linked with both the windings. So you know that whenever we have to draw the phasor diagram of any system, then first of all we have to consider a reference axis, right? Any parameter on the reference axis. जैसे कि हम लोग RLC सर्किट जब पढ़ रहे थे यूनिट 2 में, then we have considered the voltage drop across the resistor or the current flowing through the RLC series circuit on the reference axis, right? So here, since flux is common, so for simplicity we will consider the flux phi on the reference axis. तुम कहीं भी ले सकते हो, you can also consider it in the vertical direction, no problem, right? So now if we have considered flux on the reference axis in this direction, then can you say what will be the direction of the induced EMF in the two coils in this phasor diagram? किधर होगा? We have already discussed in the last class.
90 डिग्री ऊपर,
ऊपर या नीचे?
ऊपर.
फ्लक्स हम लोग कंसीडर क्या किए थे? phi m sin omega t. Then we have calculated E1 and E2. So we have found that the phase relationship between the induced EMF and the flux was such that it was sin omega t minus pi by 2. It means that the induced EMF will lag the flux, core flux, by 90 degree. That's why it will be in this direction, 90 degree lagging with respect to the transformer main flux or core flux. So here you will have, suppose if we consider a step down transformer, then E1 will be more, the magnitude of E1 will be more and E2 will be less. If it is a step down transformer, means when N1 is greater than N2. लिखी दो इसको for N1 greater than N2, but both will be in the same phase, right? ठीक है. Now tell me, what will be the direction of the source voltage or the applied voltage V1? V1 किधर होगा? Just here I have mentioned V1 will be approximately equal to the induced EMF across the primary coil, but in opposite direction. That is, it will be 180 degree out of phase with respect to E1. This will be V1, right? ठीक है. Now V2 will be equal to E2 because we have considered open circuit condition, that is no load is present here. So the current flowing through this winding will be zero, so no drop will be there, and hence both will be equal, right? So we have expressed the or represented the flux, induced EMF, as well as the applied voltage in the phasor diagram. Now we have to represent the currents, right? So when we are considering the open circuit condition, then only no load current is flowing, which is equal to I naught. So this entire I naught, the function of this entire I naught is to develop the what? हेलो हेलो, आवाज आ रही है?
Yes sir.
Yes, sir.
Okay. Okay, okay. So the main objective of this no load current or function of this no load current I naught is to develop the flux, useful flux in the transformer core. And if we also consider the core loss taking place in the transformer, because at no load condition also the losses will occur in the transformer. That loss will be basically your core loss, right? Core loss component hoga. So can you say what will be the direction of I naught? But before that, you should know that I naught will have, that is no load current, will have two components. I naught will have two components. First one, let us consider, is IM, and second one will be IC. IM is the component of no load current which is responsible for the generation of flux. And let us consider IC is the current which is responsible for the different losses, core losses taking place in the transformer, right? So can you say what will be the direction of IM? बताओ भाई. Okay, I will tell you. IM will basically lag the voltage V1 by 90 degree. ठीक है, क्यों? Because you know that in a lossless inductor coil, the current lags the applied voltage by 90 degree. ठीक है, तो ये I naught, which has two component, is flowing through the primary coil because of the application of this source voltage or input voltage V1. तो जो IM होगा, that will lag the applied voltage by 90 degree. In other way, you can also think about it, that IM is basically producing the field flux phi, or not field flux, core flux phi, right? So since we are considering a ideal transformer, ठीक है, practical transformer अभी consider नहीं कर रहे हैं, so there will be no hysteresis effect, right? If there is no hysteresis effect, therefore the phase difference between the flux and the IM will be same. That's why IM will be along the flux axis, right? अब ये IC जो है, this is the another second component of the no load current, which basically which is included in the transformer circuit or transformer design for incorporating the core losses or losses taking place in the core of the transformer. So there will be a 90-degree phase difference between IC and IM, and the resultant of these two, IC and IM, that is addition, phasor addition of these two, is your total no load current, which is I naught, right? JIM, IC plus JIM, right? That is the primary current, no load current here has two component, which is IM and IC. So IM lags behind V1 by 90 degree, right? IM is responsible for the production or development of the flux in the core of the transformer, which basically links both the winding, right? And this IC is responsible for the core loss taking place in the transformer. So basically, your V1 IC product, the product of V1 and IC will give you the total core loss taking place in the transformer, right? तो यहां से अगर हम लोग, if we consider this angle as no load angle, phi naught, that is the angle between the applied voltage V1 and the no load current, then you can write I naught cos phi naught is basically equal to IC, and I naught sin phi naught is equal to IM. तो तुम्हारा I naught जो हो गया, that is equal to on IM square plus IC square का under root, right? So this is basically your phasor diagram of transformer at no load. ये समझ में आया सबको? यस और नो बताओ भाई, उसके बाद आगे बढ़े.
Yes, sir.
Yes, sir.
Okay. Now we will draw the no load equivalent circuit diagram of the transformer. Now all of you can draw it. तो बताओ कैसे होगा नो लोड इक्विवेलेंट सर्किट डायग्राम. So first of all, let us draw the two windings of the transformer, two coils जो हैं. Right, and here we have suppose induced EMF E1, here we have E2, N1 and N2 we have considered as the turn of the two windings of the transformer, and this symbol is for the magnetic coupling between the two windings, vertical lines. Now here we are applying the source voltage or input voltage, suppose V1, right? Then here we have current, no load current. Now what we have discussed, this I naught has two components, IM and IC. So you know that the inductive current, this is basically IM is your inductive current, so we will have to use an inductor in the circuit. So this is suppose your XM, right? And the current flowing through this XM is IM. Now another component of no load current I naught is IC, right? So you know that if this here IM is inductive current, and what about this IC? This is in phase with the applied voltage V1. It means that it is a resistive current, that is current flowing through a resistor. And also you can understand in this way that ये जो है तुम्हारा there is 0 degree phase difference between V1 and IC. So since it is a resistive current, therefore we will have to represent it flowing through a resistor. This is IC and this is your I naught, right? ठीक है, ये हो गया तुम्हारा V naught यहाँ पे, sorry V2, which will be equal to E2. So this is the circuit diagram of an ideal transformer, equivalent circuit diagram of an ideal transformer. ठीक है, इसमें बताओ किसी को कोई कंफ्यूजन?
No, sir.
ओके, ठीक है. So this is about the transformer operating at no load condition. So now we will discuss the this is same thing which is mentioned in the slides, that operation of the transformer at no load condition. We have already derived these conditions in the previous class. The same thing in terms of the two terminal voltage, right? So now we will consider the second case. Second case, when load is connected across the secondary terminal of the transformer, right? This is the load which has been connected across the secondary winding or output terminal of the transformer. Then we will discuss the performance of the transformer, and that is basically the working principle of the transformer for this condition. Just a minute, wait karo. हेलो। वो 28 जनवरी वाला मीटिंग का ना सर, वो मीटिंग मैं अटेंड नहीं कर पाया था सर। वो उस दिन मैं कहीं बाहर निकल गया था शाम में। नहीं तो मीटिंग में नहीं थे, फिर भी क्या उसमें साइन करना पड़ेगा क्या? चलिए ठीक है, हम देख लेते हैं। ठीक है, अभी क्लास में अगर हम बात करते हैं बाद में। Okay, so now how the operation of the transformer will change after the connection of the load, we will discuss that. तो इसमें बेसिकली हो क्या रहा है, देखो कि we have connected suppose a load impedance of ZL magnitude across the secondary terminal of the transformer, right? So since the winding impedance, I already mentioned earlier that the winding impedance is very less. Therefore, in this case also, you can say that V2 will be approximately equal to E2 in magnitude, right? But it will be have some difference in the value because of the presence of the impedance of the winding, right? But it will be approximately equal, right? So now when load is connected, then a current will flow through the secondary circuit also, that is I2. यहाँ इससे पहले का हम लोग परफॉर्मेंस अब फिर से दोबारा रिपीट नहीं कर रहे हैं, इसमें सेम होगा। V1 अप्लाई करेंगे, then a current will flow, that current will produce I0, I1 will change, right? Hello.
Yes, sir.
Hello.
Yes, sir.
नेटवर्क इशू हो जाता है बीच में, चलो ठीक है। So the magnitude of the primary current will be more in this condition because of the presence of the load connected across the secondary terminal. How it increases, that we will discuss now. So a current I2 will start flow through the secondary winding when the load is connected across the secondary circuit, that is I2. Now you know that if any current flows through any coil, I2 अगर flow कर रहा है secondary coil के cross having N2 number of turns, then what will happen? It will also produce its own flux. पहले से एक flux है phi, which is developed because of the flow of current I1 through the primary coil. Now an EMF has been induced across the secondary coil due to the flux linkage in it. So that EMF will also cause a current to flow through this circuit, that is I2. Now this I2 will also produce a flux F phi2, ये जो phi2 मेंशन किया गया, ठीक है? But what should be the direction of the MMF generated due to the current I2? Again, Lenz law should be applied here, right? So according to Lenz law, the direction of the secondary current I2 should be such that the secondary MMF here will be N2I2. The direction of this current I2 should be such that the secondary MMF F2 is opposite to the mutual flux. ठीक है, यहाँ पे इफेक्ट क्या है? Effect is the development of MMF, or you can say flux. Both are directly proportional to each other. So effect is F2 and the cause is this flux phi, because flux linkage की वजह से EMF आ रहा है और EMF की वजह से current आ रहा है. So the direction of current to the secondary circuit will be such that the secondary MMF is opposite to the mutual flux phi in the transformer core. Right? अब ये बताओ हमको कि जैसे कि ये जो है फाई 2 या F2 कब अपोज करेगा फाई को? When the direction of current is in this direction as mentioned in the circuit. Because क्या हम लोग पढ़े थे कि कहीं भी फ्लक्स का डायरेक्शन कैलकुलेट करने के लिए या एस्टिमेट करने के लिए यू हैव टू पुट योर थंब in the direction of current. So put your thumb in the direction of current. So you will find that flux is in the opposite direction of the main flux flowing through the transformer core. That is phi. Right? ठीक है, ये समझ में आया? So for F2 to be in a direction opposite to the flux phi, the current I2 must leave this terminal. Suppose if we represent this terminal by A and this terminal by B, तो ये होगा A टर्मिनल को लीव करना चाहिए और B से इंटर करेगा. ठीक है. So the secondary MMF F2 is opposite to the flux phi. So it will tend to reduce the mutual flux phi. Obvious, it is quite obvious that there is existence of an additional flux phi 2 which is in the opposite direction of flux phi. Suppose phi इधर है और phi 2 इधर है, so the net resultant flux will be reduced in the transformer core, right? But any reduction in this phi will reduce the induced EMF across the primary winding, that is E1. अगर phi reduce करेगा, it means E1 also reduce करेगा, right? And you know that for an ideal transformer, for any ideal transformer, V1 is equal to minus E1. अभी just हम लोगों ने देखा है, ठीक है? So if the applied voltage V1 is constant, because that is your applied voltage, उस पे हमारा कोई control नहीं है. If your applied voltage V1 is constant, therefore E1 and the mutual flux phi in the core must remain constant. अगर V1 constant है तो E1 constant होना चाहिए. और E1 कब constant होगा? When your flux is constant. तो ये कैसे होगा? This can happen only if the primary winding draws more current from the source, so that it can neutralize the effect of the secondary MMF F2. ठीक है? तो होगा क्या कि अर्लियर मान लो प्रीवियस केस से अगर कंपेयर करें, देयर वी हैव कंसीडर्ड द नो लोड करंट. सो हियर एन एडिशनल करंट I1, suppose I1 dashed is taken from the source. So the equivalent of this I0, that is no load current, and the additional current drawn by the source is equal to I1. राइट पहले क्या था, जब नो लोड पे ऑपरेट हो रहा था, देन ओनली नो लोड करंट I0 वाज फ्लोइंग. बट नाउ ड्यू टू द प्रेजेंस ऑफ द लोड और कनेक्शन ऑफ लोड, an additional current I1 dash is taken from the source, and the net resultant current is your primary current I1. So the function of this I1 dash additional current is just to neutralize the demagnetizing effect of the secondary MMF N2I2, right? So in this manner, the current I2 basically causes the primary to take more current, additional current, which is equal to I1 dash, right? So the function of this I1 dash is to just neutralize the effect of I2, and this can happen only if I1 dash N1, that is the MMF of the primary side, is equal to MMF of the secondary side. So if this effect is neutralized, only then your total flux in the core will remain constant, right? इसका मतलब क्या हुआ इस एक्सप्रेशन का? इसका मतलब हुआ कि secondary MMF is equal to compensating primary MMF. ठीक है? So the conclusion is that any change in the secondary current, is reflected by the corresponding opposite change, automatic change in the primary current in order to make the core flux constant. ये समझ में आया ऑपरेशन की नहीं समझ में आया बताओ, फिर आगे बढ़े हम लोग. इसमें किसी को कोई कंफ्यूजन?
No, sir.
No, sir.
Because this is an important aspect in the transformer operation at no load condition. I will just repeat once because some of you may not have understood completely. So in short I will repeat. देखो लोड जब नहीं कनेक्ट था सिस्टम में, during that time you know the operation कि we apply the source voltage across the primary side, so a current flow through the primary coil which produces a flux produce होगा, ठीक है? So due to the linkage of that flux with the primary coil, an EMF E1 will induce across the primary coil, right? Now that flux also links with the secondary coil, right? And some EMF E2 is induced across the secondary winding. Now when we connect the load, so a current will flow through the secondary circuit, right? Now main thing is the direction of the current. So the direction of the current I2 should be such that the MMF produced due to this current I2 in the secondary coil should oppose the cause, which is the flux as per Lenz's law. So the opposing flux will have a tendency to reduce the main transformer core flux, that is phi. ठीक है? अब अगर phi reduce होगा, then it means that there will be a reduction in E1 because flux phi के linkage से E1 induce हो रहा था primary coil के across, ठीक है? And if E1 will reduce, then what will happen? It will directly affect the source, क्योंकि source voltage जो है वो equal in magnitude to the induced EMF across the primary coil, that is E1. So in order to make this E1 and phi constant, you will have to take more current, additional current from the source, that is I1 dash, ठीक है? तो अगर हम I1 dash की वजह से जितना MMF हो रहा है, that is I1 dash N1, and if this MMF is able to compensate the demagnetizing effect of the secondary MMF, that is N2I2, then your core flux will remain constant, right? So this is the complete working principle of a transformer operating at load condition, when load is connected. So same thing is expressed through these slides. वही ऑपरेशन है, I1 इंक्रीज करेगा तो phi1 इंक्रीज करेगा, ये सब I have already expressed and discussed these things, ठीक है?
सर वो
हाँ।
प्राइमरी कॉइल का सर इम्पीडेंस कांस्टेंट है, तब भी सर करंट कैसे इंक्रीज कर जाएगा?
हम्म।
सर मतलब जैसे
क्या बोल।
प्राइमरी कॉइल का सर इम्पीडेंस तो कांस्टेंट रहेगा, तो भी सर मतलब प्राइमरी करंट सर इंक्रीज क्यों करेगा? मतलब वो प्राइमरी करंट मतलब तब इंक्रीज करना चाहिए था जब इम्पीडेंस
नहीं,
घटता।
यहाँ पे यहाँ पे जो है सो वाइंडिंग इम्पीडेंस की वजह से कोई करंट इंक्रीज नहीं हो रहा है। द करंट इज इंक्रीजिंग बिकॉज यू आर कनेक्टिंग द लोड अक्रॉस द सेकेंडरी टर्मिनल। फॉर एग्जाम्पल, you can consider this effect. Suppose you have in your room you have uh, two fluorescent lamp and one fan, one AC, right? अब अगर तुम उसमें एक हीटर भी ऐड कर दोगे, मीन्स लोड इंक्रीज कर दोगे, सो ऑब्वियसली द लोड करंट विल इंक्रीज। तो लोड करंट जो इंक्रीज होगा, इसका मतलब क्या होगा? वो कहाँ से आएगा? सोर्स से ही तो आएगा। हम्म।
यस
लोड
सर।
के इम्पीडेंस की वजह से इंक्रीज हो रहा है करंट, ना कि वाइंडिंग की रेजिस्टेंस की वजह से। वाइंडिंग का रेजिस्टेंस इज ऑलवेज कांस्टेंट फॉर ए पर्टिकुलर ट्रांसफार्मर।
ओके
ठीक है।
सर। यस सर।
ओके। So same thing is expressed through the in these slides, the same effect, counteract or opposing effect, balance कैसे होना चाहिए दोनों के बीच। So this is about the working principle of complete working principle of the transformer, right? So now before we discuss about the practical transformer, हाँ, इसमें अगर ये अब तुम लोग कह सकते हो कि फेजर डायग्राम अगर ट्रांसफार्मर का बनाना चाहो लोडेड कंडीशन में, सो यू ट्राई टू ड्रॉ दैट, ट्राई टू ड्रॉ द फेजर डायग्राम एट लोडेड कंडीशन। उसके बाद हम लोग ये टॉपिक पे आएंगे। ये समझ गए हो? इसके बाद हम लोग कंस्ट्रक्शन के बारे में पढ़ेंगे, थोड़ा ट्रांसफार्मर कंस्ट्रक्शन, एंड देन वी विल टॉक अबाउट द प्रैक्टिकल ट्रांसफार्मर्स वेयर वी विल कंसीडर द इफेक्ट ऑफ लीकेज flux also, as well as the different winding impedances also, resistances also. बनाओ भाई, फेजर डायग्राम बनाओ तुम लोग। अभी नो लोड के कंडीशन में बनाए थे, अब लोडेड कंडीशन में बना के देखो क्या आता है। फिर सर्किट डायग्राम बनाओ। कैसे करेंगे बताओ? Again, start from the basic that flux is common, phi is common to both the circuit. So let us ये क्या चक्कर है? हाँ, since phi is common to both the circuit, so take the flux phi on the reference axis. ठीक है? So if we ignore the winding impedance, जैसा कि हम लोगों ने अभी डिस्कस किया था कि E2 will be approximately equal to V2, right? But practically V2 will be slightly less than E2, ठीक है, due to the presence of the winding impedance. So here again E1 and E2 जो होगा, सपोज ये E1 है, अगर मान लो कि ये E2 है, so both will be 90 degree phase lagging to the flux, core flux of the transformer. E2 will be equal to V2, ठीक है? So here V1 होगा इधर फिर से, ठीक। Now we have a secondary current I2. I2 will lag E2 or V2 by some angle, phase angle, because mainly it has inductive, mainly the coil is inductive in nature. So suppose this is I2, ये एंगल मान लो कि है phi 2, एंगल बिटवीन V2 एंड I2 is phi 2, ठीक है? अब ये बताओ, पहले हम लोग ये जो नो लोड कंपोनेंट है, हियर I1 बेसिकली, I1 जो यहाँ पे है, इट हैज टू कंपोनेंट, यू नो, I0 प्लस I1 डैश, वी हैव ऑलरेडी डिस्कस्ड दैट। अब I0 का ऑलरेडी यू हैव टू कंपोनेंट, IM प्लस J, सॉरी, IC प्लस JIM। तो IM किधर है? इधर है, जैसा कि नो लोड फेजर डायग्राम में बनाया। IC इधर है। द इक्विवेलेंट ऑफ दीज टू इज योर I0। Now what will be the direction of I1 dash? I1 dash किधर होगा ये बताओ। बताओ।
I2 के अपोजिट।
Right, it will be just in phase opposition, equal in magnitude and in phase opposition to I2. Why? Because it is counteracting the effect of I2। ठीक है, जो MMF को न्यूट्रलाइज कर रहा है, द सेम थिंग। ये रिलेशन याद करो अभी जो पढ़े हैं, I2 N2 is equal to I1 dash N1। Now the resultant of these two, I1 dash and I0, is basically your total input current or primary current, that is I1। ठीक है, तो V1 और I1 के बीच का एंगल जो है, इसको मान लो phi1, और V1 और I0 के बीच का एंगल तो हम लोग पहले ही डिस्कस कर चुके हैं, दैट इज द phi नॉट। ठीक, तो दिस इज द फेजर डायग्राम ऑफ ए ट्रांसफार्मर ऑन लोडेड कंडीशन। ठीक है, समझ में आया? फेजर डायग्राम ऑफ ट्रांसफार्मर ऑन लोडेड कंडीशन लिख दो, या कुछ भी लिखो अपने हिसाब से। किसी को कोई कंफ्यूजन है इसमें तो पूछ सकते हो, otherwise we will move ahead। I think there is no question। So now after discussing the ideal transformer working principle both at no load and loaded condition, we will discuss about the types of transformer। So basically there are two types of transformer depending upon the construction of the core used in the inside the transformer। So first one is your core type transformer, second one is your cell type transformer, right? So you know that when we have discussed this magnetic circuit, first part of this chapter, then we have seen that the core is basically made up of thin silicon steel lamination sheet, which has the thickness of around 0.35 to 0.4 mm for 50 hertz system। We will only talk about 50 hertz system because in our India it is 50 hertz। अब दूसरे कंट्री में देखोगे, यूएस में जैसे 60 हर्ट्ज ऑपरेशन होता है। सो देयर द कंस्ट्रक्शनल डिटेल्स ऑफ द ट्रांसफार्मर कोर may be different, right? So the transformer core basically is made up of thin silicon steel lamination sheet, and all these thin sheets are combined and stacked together to form the complete cross section of the transformer core। So there are various benefits of using the laminated sheets while designing the transformer core। We have already discussed that first one is your reduction of the eddy current losses, how eddy currents are generated in the transformer core we have seen। And then another advantage is that with the help of the some good quality silicon steel sheets, we can also reduce the effect of hysteresis loss, that is the core loss, which basically consists of two components, eddy current loss and hysteresis loss। So both can be reduced if we are using silicon steel laminated sheets. So in the next class, we will discuss in detail about the construction of the transformers for both types, core type and cell type. And then we will discuss about the construction of transformer cores with the help of CRGOS sheets. What is the property and how the laminations are actually made, because in actual practice we don't have this thickness of laminations. We have to cut these laminations from magnetic materials, right? तो कैसे कटिंग किया जाता है, किस एंगल पे कटिंग किया जाता है, so that we can get the best magnetic property of the transformer cores. So all these things we will discuss in the next class, right? So if you have any question you can ask, otherwise I will end this meeting now. Any question?